Hey guys, I'm Pat Kelly. Okay, in this problem, they ask us to use partial fractions to evaluate the definite integral. Okay, so they've already given you a little bit of a hint, might be more than just a hint. They beat you over the head and said we're going to use partial fractions. So the right place to start is to take that denominator and factor it, and that's going to lead us to the expression we need in order to do the partial fraction decomposition. So that trinomial in the denominator does factor. Might not have thought to do that on your own, but again, they told us it's going to be partial fraction decomposition, so you know the denominator is going to factor. So I'd be looking at factoring this, which I'm thinking works with a 4x and an x, and it's got to be plus 1, plus 1. Check your FOIL, and it works. Okay, so the original integral exactly equals that, but that version of the rational expression is better suited for me for the partial fraction decomposition work that I'll do now over here. So let's just use our space over here just to use the partial fraction. If I say D, partial fraction decomposition, I'm just going to grab that fraction, 3 divided by the 4x plus 1 times x plus 1. Okay, so the factored version of that rational expression, and we set that equal to, and your setup for partial fraction breakdown is to look at each of the factors in the denominator. In this case, the first one is just 4x plus 1. And since that's linear, all I do is put an a up top. Since that factor of 4x plus 1 only occurs once, I only need one fraction to represent it. And then I move on to the next factor of x plus 1. And again, since that's linear, all I need up top is a b. That's it for my factors in the denominator, so that's it for my setup for the partial fraction decomposition. Now you do your algebra to play around and find those exact values for a and b. So I multiply the entire equation by that denominator, and what happens on the left is I just get the numerator of 3, and on the right-hand side, the first fraction has 4x plus 1, which is going to cross out with that 4x plus 1, so the a only gets multiplied by the x plus 1. Let's go ahead and do that multiplication, ax plus a. Second fraction, the x plus 1 would cross out. All I'd be left multiplying that b by is the 4x plus 1. So let's write that as 4bx plus b. Look okay? All right, and then the deal with the partial fraction work that you do at this point, I always see it as a bit of a balancing act. And so on the right-hand side, look how many x's you have. I have a plus 4b x's. And on the left-hand side, I have no x's. So that tells me that a plus 4b has to equal 0. Still thinking about a balancing act, look at how many constants you have on the right-hand side. I have a plus b. A plus b on the right-hand side has to balance with the constant on the left-hand side, which is just 3. So a plus b is going to have to equal 3. Okay? And then what you end up with the partial fraction work that you do is a system of linear equations in terms of a and b, and c and d if you had more unknowns. But you solve this system of linear equations to find your exact value for the a and the b. So in this case, I think what I'll do is subtract these two equations. Maybe I'll even slow down real quickly and say, you solve the system of linear equations however you want, okay? I'm doing an elimination method. You might do substitution method. You might throw it into a matrix. You do whatever you're comfortable with. But here, I think I can get away with some pretty easy work if I just subtract. A minus A is gone. 4b take away b is 3b, and then 0 take away 3 is minus 3. So I'm getting a value for b of -1 without too much work. And then I'll resubstitute that b, take this b equals -1 and plug it in here. So a minus 1 equals 3. So a equals 4. You get your exact values for the a and the b that are your numerators on the right side of the equation here. So now you come back to your original work here. You get back to calculus class, but you substitute with the algebra that you did, this integrand, all right, equals, I still have 0 to 2, but that entire expression on the inside of the integral gets replaced with these fractions, but with my specific values for a and b. So my a was 4 over, I'm looking at this fraction, 4x minus 1, 4x plus 1. And I'm still looking at this right-hand side of the equation. There's a plus b up top, but my b was -1, and the denominator was x plus 1. Let me put a nice set of parentheses there because that's all inside my integral, dx on the outside of that. And the whole point of partial fraction decomposition when you're doing integrals is you take something that maybe is not too easy to integrate, well, let's just admit that's pretty darn hard, and makes it smaller fractions that are maybe more manageable for you to integrate. So I'm ready to actually integrate this. The 4 would come out in front, and then that, I think I might write this one. That 4x plus 1, I'm actually even seeing as a u substitution. So du equals 4 dx. Kind of stopped myself there because I said something about the 4 out in front, but I think I actually like that 4 where it is because it's a part of the 4 dx. So that's just going to be a du over u. Okay. You could do a u substitution, a different u equals for this bottom one, but if you let u equal x plus 1, sorry, you could do a different u equals for this second fraction and let u equal that bottom one, but u equals x plus 1, the du is going to be equal to dx. That doesn't really simplify at all. This will end up equaling the 4 dx just becomes du. This is du over u for this integral. I'd still have this second fraction. Let me write that as minus the integral dx over x plus 1. Okay. And I do still have these limits of integration, but I think I'm going to hold on to those for a second and resubstitute for u after I integrate. So I'm still going to keep those as x's. X equals 0. X equals 2, and these are still x's 2. So this equals, this is a natural log of the absolute value of u. And this is where I was saying something about resubstituting, so let's put that u back in, 4x plus 1, absolute value. Subtract, you can integrate this guy now too. Also an ln, absolute value of x plus 1. And all of that is evaluated from 0 to 2. So equals natural log, putting in a 2, 4 times 2 is 8, plus 1 is 9. I can drop the absolute values because 9 is positive. Subtract from here. Natural log of 3. I'll put parentheses there just to suggest that's from plugging in your upper limit of integration. Subtract what happens when you plug in your lower limit. So now I'm putting a 0 in. Natural log of 1 minus natural log of 1. Maybe you thought of this already, but natural log of 1 is 0. There's another 0. So this just comes down to the natural log of 9 minus the natural log of 3, which equals the natural log of 3 if you use a property of logs. Do you remember one way to look at it is subtraction between logs is division of the argument. So you could have 9 divided by 3. That's how I'm getting just 3 in a single logarithm. Okay, that's really good. And I'd be happy with that answer. But in this problem, they do actually also ask us to verify using a graphing utility. So I'm going to take that natural log of 3 and write its decimal approximate value just so I can compare it to the graphing utility. Okay? So grab a calculator to calculate the natural log of 3. We're thinking ahead a minute. We're going to need a graphing utility if you just want to jump right onto one of those. Either way, let's type in the natural log of 3. And if I round, I guess maybe to 3 decimal places, 1.099. That's just something to anticipate then. Hopefully our graphing utility will confirm that. So let's see. Second half of the problem then is to confirm this using a graphing utility, which means you go back to the original expression and you're actually just grabbing that integrand expression. Put that into your y equals in your graphing utility of choice. We type mine in 3 divided by 4x squared plus 5x plus 1. Group the denominator. I'm going to graph mine. I see the graph of it. I'm going to zoom in once. See it a little bit more closely. Okay, and then in order to verify our 1.099, now we use the integration features of your graphing utility. I'm going to go to my calculus menu, a lower limit of 0, upper limit of 2. My utility has to think for a little bit, and then it displays 1.0986, exactly the same thing I have with rounding. Okay, that's how I would do this problem. I hope that helps you do some more problems on your own, okay? Thanks.